Well, hey there. If you're watching this video, you must have had a little trouble understanding what your teacher was saying when they were going over radiometric dating. And that's pretty common, so don't feel bad. My name's Sharon Gable, and I'm here to help you try to understand it a little bit better. On the right-hand side, we have the structure of the atom, and I'm sure you know that the nucleus of the atom contains neutrons that have no net charge and protons that are positively charged. Around the atom are whizzing these tiny little electrons. Each electron has a negative charge to it. The atomic mass is the sum of the number of protons and the number of neutrons in the atom. Why is that? Because each neutron has a mass of 1 atomic mass unit and each proton has a mass of 1 atomic mass unit, and electrons don't weigh hardly anything, so they don't even count. You probably learned somewhere along the line that it's the number of protons in the nucleus that determines the identity of an atom. In other words, it determines what element the atom is. So every atom of a particular element has the exact same number of protons. Isotopes, on the other hand, are atoms of the same element, so obviously they have the same number of protons in their nucleus, but they have different numbers of neutrons. A simple example is to compare two isotopes of carbon, carbon-12 and carbon-14. Every atom of carbon has 6 protons in its nucleus. Carbon-12 has 6 protons in its nucleus, of course, and it also has 6 neutrons. So 6 plus 6 equals 12. That number 12 is the atomic mass of the isotope. So what about carbon-14? Has to have 6 protons in the nucleus. How many neutrons do you think it has then? So yeah, the carbon-14 has 8 neutrons in its nucleus. Carbon-14 is interesting because it's a radioactive isotope. What's a radioactive isotope or radioisotope? Well, that's an isotope that will spontaneously decay, and when it does, a different isotope forms, and in the decay process, radiation is given off. Let's see how carbon-14 does this magical thing. Well, remember the carbon-14 has the 6 protons and 8 neutrons in the nucleus, and when it undergoes that spontaneous decay, one of the neutrons in the nucleus breaks down actually, and that gives off an electron and becomes a proton. So the electron that's given off is the radiation. And what we have as a result of the decay is a new isotope that has 7 protons and 7 neutrons in the nucleus. If it has 7 protons, it's got to be nitrogen, and 7 plus 7 is 14. So that's nitrogen-14. Of course, not all isotopes are radioactive. The nitrogen-14 that forms when carbon-14 radioactively decays is not radioactive. It's a stable isotope. So stable isotopes do not undergo that decay process. All right, so it's a simple thing to remember. When a radioactive isotope decays, a stable isotope forms. And when I go over radiometric dating, I like to call the radioactive isotope the parent and the stable isotope the daughter isotope. Sometimes the radioactive decay to form the stable isotope is not a one-step process. That's why the eventually is in there. For carbon-14, it was a one-step process. Carbon-14 decays, boom, you have stable nitrogen-14. But what about uranium-238? It's a commonly used isotope in radiometric dating. And the stable isotope that forms when uranium-238 decays is lead-206. But it is not a one-step process. And this diagram here that's inscrutable, you can't read it, it starts out up here with uranium-238, And there's a whole bunch of different decay steps, right? In each of these steps, a new radioactive isotope is forming. And eventually, lead-206 forms, and that's not radioactive. It's a stable isotope. So that's the end of the line. All right, now how fast does this all happen? You see, we can't be certain exactly when a given atom of a radioisotope is going to, bing, undergo radioactive decay. But we can take a whole bunch of radioactive isotopes, this the same radioactive isotope. We can't just have one atom of it. You have like a whole jar. Think about a whole jar of uranium-238. Uranium-238 is a pretty stable radioactive isotope. What that means is it doesn't decay very fast, right? It takes a while for one atom in the jar of uranium-238 to undergo decay, and then it'll be a while before another one undergoes radioactive decay. Whereas other radioisotopes are more unstable, and something like radon gas. Radon is radioactive gas. You have a jar of those atoms. There's going to be one popping off and undergoing radioactive decay, in other words, very frequently. Now, so we can't say exactly when a particular atom will decay, but we can say if we have a whole bunch or population of atoms of a radioisotope, they're going to decay either at a faster or a slower rate. Radon gas is pretty unstable, and if you had a whole jar of those atoms, within 4 days, half of the atoms will have decayed, right? Become stable isotope. And then we can compare that with a much more stable isotope like uranium-238. It would take 4.5 billion years for half of them to decay. Okay, so this is where we get the notion of half-life. Half-life is the way we measure the rate of radioactive decay. It's the time it takes for half of a sample of a particular radioisotope to decay and become stable isotope. And thank goodness that half-life for a particular isotope, it's constant. Doesn't change over time, doesn't change as a result of really high temperatures, really high pressures, so we can be sure that the rate at which atoms of a particular radioactive isotope are decaying has been constant through time. Let's just remember a few basic ideas. As time goes on, right, if we have a jar of, or a bunch of radioactive isotopes in a mineral in a rock, we have a certain number of parent isotopes in there, and as time goes on, the number or the amount of parent isotopes is going to decrease as they decay, while the amount of daughter isotope atoms that form as a result of the decay of the parent increases over time. So when it comes to radiometric dating, we're usually looking at the ratio of parent isotope to daughter isotope in a particular mineral that we isolate out of a rock, because it's that ratio that indicates how many half-lives have gone by. And since we know the half-life of our different radioisotopes, we can use the number of half-lives to just do simple arithmetic and find the age of the mineral itself. Okay, so very simple concept. The more time goes on, the less radioactive parent you're going to have, the more daughter you're going to have. So that ratio of number of parent to number of daughter isotope is going to change systematically over time. So let's talk next about how we can use all this gobbledygook to figure out the age of a rock.